Yes, you are.
Yeah, okay.
Nice. Nice. Perfect. Sir,
Yeah,
A very good morning to everyone. I welcome you all the third day of 5-day faculty development program on additive manufacturing and industrial scope and applications. Today's first session, computer-aided design and simulation of machine parts for additive manufacturing using Solidworks by Dr. Rajendra Machavaram. Few words about today's speaker. Dr. Rajendra Machavaram, Assistant Professor, Agricultural and Food Engineering Department, Indian Institute of Technology and Technology, Kharagpur, West Bengal, India. He received his doctorate degree in 2014 from IIT Madras, specializing in machine design, and Master MTech from IIT Kharagpur in 2008, specializing in the area of farm machinery and power. He worked from June 2008 to April 2010 as research and development member at the TAFE R&D Center, Chennai from June 2014 to October 2014 as assistant professor at SRM University, Chennai, and from October 2014 to June 2016 as a visiting faculty at IIT Kharagpur. He is currently working as assistant professor in the Department of Agricultural and Food Engineering of the Indian Institute of Technology, Kharagpur, that is IIT Kharagpur, in farm machinery and power specialization from June 2016. His research interests are machine design, design optimization, artificial intelligence, farm power and renewable energy, damage identification, and evolutionary algorithms. His 5 recent publications I like to share with you. The title is the recent publication, Measurement of Morphometric Dimensions and Mechanical Properties of Raw Fish for Design of Processing Machines, Journal of Aquatic Food Product Technology. The second one, the title of Injection Molding Process Optimization of Biaspheric Lens Using Hybrid Artificial Neural Networks. It means that ANNS and particle swarm optimization measurement. The next, International Journal of Agricultural Science, he published in the title of Computer-Aided Design of Farm Implements Using Visual Basic Program. Next, the recent publication, the performance of a diesel engine with water emulsified diesel prepared with optimized process parameters in the Journal of International of Green Energy. The next one, combustion behavior of diesel engine operated with water emulsified diesel, Journal of Scientific Research and Reports. This is the limited papers I shared with you. He published a number of papers. We are very happy with us, Dr. Rajendra Machavaram. I welcome you, sir.
yeah. Is it audible from my side?
yes,
Yes,
sir.
sir.
Okay, thank you. Yeah, thank you for your kind words, the team, Noida Institute of Engineering and Technology. And I am very much happy to participate in your training program, the 5 days faculty development program on additive manufacturing and industrial scopes and applications under ATAL scheme.
We are glad for
This is
this,
the
sir, to have you with
topic
us.
I'm going to present. That is computer-aided design and simulation of machine parts for additive manufacturing using SolidWorks under this 5 days faculty development program on additive manufacturing and industrial scopes and applications, organized by Noida Institute of Engineering and Technology, Mechanical Engineering Department under AICTE Training and Learning Academy. Now, if you observe the additive manufacturing from past 2 days, you might be just going through the different aspects of additive manufacturing. I've just kept it as a brief about it. The additive manufacturing, also referred to as 3D printing, is a process of fabricating parts by creating successive cross-sectional layers of an object. In this case, we are just adding the material without any deletion or without any removal. As we do in the conventional manufacturing process, we have a block, then that block we are manufacturing with different processes. Like we have a turning and drilling and all. There we are removing the material. But in this additive manufacturing, we are just adding the material. And this is very important technology nowadays because of the available computational power like computers, and from there the digital technology has come, and we are taking that one towards the manufacturing using the CNC machines or our 3D printers. If you observe the applications, we have this additive manufacturing applications in automotive, aerospace, engineering, medicine, biological systems, and food supply chains. Even in the food processing technology, there are different machines we are developing for making the 3D printing of food products or molding and all those things. Now, actually, how this technology has come is that this technology has been developed by Charles Hull in 1986 in a process known as stereolithography (SLA). From there, the development has started to powder bed fusion, used deposition modeling, inkjet printing, and contour crafting. These are all the different technologies developed after the stereolithography, and initially the word tossed the additive manufacturing by Charles Hull in 1986. Anyway, if you observe the different classification of the additive manufacturing given by Rajaguru et al. In his paper, the additive manufacturing is classified under as a solid extrusion based, powder based, liquid based, solid based, powder based, liquid based systems. Under solid extrusion or wire extrusion based system, we have fused deposition modeling, that is FEM, FDM, wire plus arc additive manufacturing, that is WAM, and electron beam freedom, that is EBF3. These are all the three technologies available under solid extrusion. Under power based systems, we have again selective laser sintering, then electron beam melting, selective laser melting, direct metal laser sintering. Under that, each one category like selective laser sintering (SLS), we have multi-components metals alloy powder. One technology, the other technology is powder binder printers. These are also available. Under selective laser melting, we have pure metal powder, alloy powder. These two directly we can use under selective laser melting process of power-based systems. If we go with the liquid-based systems, there we have stereolithography, as I told earlier by the Hull. He was invented from this, and we have direct light processing (DLP) and inkjet printing (IJP). These are all the different classification of additive manufacturing, broadly classified based on the process, like a solid, powder-based system or liquid-based. Even based on the model, we have again 2D printing or 3D printing. These are also other two, the second classification of additive manufacturing. And ASTM, they have given the classification, American Society of Testing Materials, they have given the classification as material extrusion, power-based extrusion, wet photopolymerization, metal jetting, binder jetting, sheet lamination, direct energy deposition. These are all the different technologies given by the classification by ASTM classifiers. Here you can see the different technologies, then what is the printing material they are using, and what is the power source, and we can also see the strength and downsides of this particular technology. This was the classification given by ASTM. You can see the fused deposition as a technology, contour crafting, selective laser sintering, direct metal laser sintering, selective laser melting, electron beam melting, the technology. These four are there under power bed fusion. We have wet photo polymerization. Under this, we got stereolithography, and metal jetting. We have polyjet, inkjet printing. These two are there. And binder jetting, we have indirect inject printing. That is the binder. 3DP is also available under binder jetting. The sheet lamination, we have laminated object manufacturing (LOM), and the direct energy deposition, we have the technology as laser engineered net shaping or electronic beam building. This is the broad classification. You can also observe like the strengths and downsides of the each technology, and the power source as a for each technology, which power source is required for doing this particular 3D printing. We can observe in this particular classification. Now, the same additive manufacturing as a process flow, we can categorize as a direct method or as an indirect method. In the indirect method, we have an object. That object we are scanning using as a CT scan or MRI, and from there we can get directly as a 3D CAD modeling. If the object is available, that is called as reverse engineering. If we don't have an object, initially the object or the model we are just designing. For that we have a design concept. From the design concept, we have to think what product we are making and what are the different parts, how these parts are assembled together to form as an assembly, and that assembly will be used for the functioning. And in this particular assembly, we are making a 3D CAD modeling, and those 3D CAD models we are again using for the analysis, whether the models are strong as per the strength, and as per the functionality also we have to test, and even required we have to do for the optimization. Optimization means saving the time as well as the saving the material. Using this optimization, we can just check the different dimensions or the process time and all. We can able to use the optimization technique for the analysis. Anyway, now this injection molding, where the optimization plays a major role in deciding the temperature and all for the injection molding process. Once these CAD models and analysis is ready, that one we are taking under STL format conversion, and this format conversion as a G code we are giving it to the 3D printing, and from there we are getting the models or the parts. Later on we have to just do as a post processing technique for removal of the extra materials like these and all, and finally we will take that part into our functional component or functional assembly. This is the process of additive manufacturing. Here I am concentrating on two aspects, that is the 3D CAD modeling with the design concept and analysis part. The optimization I am not covering here. Analysis part I will be covering. Now, the same thing I have indicated in terms of as a process flow, and the first one is the creation of the virtual models. Here under the virtual models, initially the model are scanned as a digital CAD file we need to generate. That generated model, we can use the different softwares like AutoCAD, Creo, Solidworks, CATIA, and AnyGraphics. These softwares we can use for making the computer-aided design models. Now, once the model is ready, we have to do the analysis, the visual analysis. We need to verify the model is as per the strength and functionality or not. Now, in this verification process, we can use the softwares again. The ANSYS also we can use. Console, Abacus, SolidWorks. These are all the softwares used for the visual analysis part. If you observe here, as given by Goa et al. 2015, he has used one the base of a chapel slipper, and we can observe that here he has modeled the a foot when it is contacting onto the shoe sole as a shoe, the sole, how the forces are distributed. You can observe the different material distribution also after meshing, and you can observe the same model with a different strength. Like we have a default, the first part, what it is available. Under this, we can observe the pressure distribution is not uniform. Once we apply a force with our foot onto the shoe sole. Now, if you go with as a uniform pressure, the different materials we can select under the model, and based on that, you can observe that the distribution of the pressure is uniform. In this particular case, as a uniform pressure. The third one is again we can divide into two partitions. One is our heel partition. The another one is our front portion of the sole of a shoe. Once we divide, because the force distribution is different, that is why whenever we are selecting a material, we can go with the two side materials where the load is coming onto the load is acting more onto the heel, but as a concentric part. But onto the front portion of the sole, the area of contact is more, but the load is more or less uniform, and it is very less. It is not like as a straight as a concentric load. It is like a uniformly distributed load. For that, if you observe the 3 times of higher pressure on the heel, we can observe the distribution of the pressure over here. And if we go with the 3 times of higher pressure in the front is there, we can also see the how much is the distribution of the pressure. Here the color indication goes from blue as the low to the high of 30 into 10 to the power of 4 pascals as the highest pressure to the red color. As I told earlier, you can observe that on the back side of that is the heel part, the color is almost nearer to the red color. That means the stresses induced in this particular location are more compared to the front portion of the sole. Now, after doing this CAD modeling and analysis part, then we need to convert that one into STL file. The models are converted into standard triangular language or STL, or it is also called as the standard tessellation language. This is the full form of the STL format. For why it is required means for slicing process. Means the slicing means the different layers we are creating while doing the additive manufacturing. Slicing and creating supports, in this case we have the slicing process is done horizontally. Always we are going with the horizontal, not as a vertical, because to reduce the process time, and we have a motion for our tool head, that is the extruder, along the x and y axis and also the z axis. Once it completes the x and y axis, then it goes to the z axis, the height. That is why we are just slicing the part into the onto the horizontal plane. Now, once the thickness is ready, this slicing and creating supports, we can use the different the softwares are available like Cura, Mesh Mixer, Blender. These are all the broadly used the softwares for slicing or creating the supports. Now, once these supports are created, then we have to convert into the G code. That is the export that file into the .gx file. Here, why we need to make this .gx file is that we need to generate the coordinates or the extruder or platform should move to along with the x and y axis and also the z axis. To do that one, we need to convert that one into as a G code. If you observe here, there are different layers. Like we can go as a thick layer print, and another one is thin layer printing. In the thick layer printing, the layer thickness is very high, but the process is very fast. That means it takes very less time. If you observe the surface quality is not smooth in this particular thick layer printing. That is why we have to either go for the thin layer. There is a tug of between the process time and quality. Based on that, we need to choose. Based on the quality, if it is a quality is a major.
Excuse me, sir.
Yes.
Sir, are you sharing a slide, sir? Actually, we are only visualizing your video, not the slide. If you are sharing, then it is not appeared here.
So from the beginning or?
From the beginning, sir.
Oh, I'm sorry. Actually, I shared the slide. What happened?
Actually, it was not visible. I thought you will be sharing soon.
Yeah, it is already I've shared. It is showing that I have shared the screen. Is it visible?
Not yet, sir. Yeah, now it's visible, sir.
Yeah, just roughly going through what the thing I have discussed. I have just defined the additive manufacturing and the application of the additive manufacturing. Further, it was tasked by Charles Hall in 1986 in his process called stereolithography, and from there the development has started. Powder bed fusion, fused deposition modeling, inkjet printing, and contour crafting. This is the classification of the additive manufacturing process. Additive manufacturing process is solid based, powder based, and liquid based. Even as per the ASTM, also the classification is there as a material extrusion, power bed fusion, wet photopolymerization, material jetting, binder jetting, sheet lamination, direct energy deposition. These are all the different categories of ASTM classification for additive manufacturing process, and the technologies also have just discussed and strengthened the demerits of that particular technology also we can observe in this particular slide. As the additive manufacturing as a process flow, we can start with as a reverse engineering. There the model is available. We just want to change the material, or we want to change some innovative fabrication over there. For that, whatever the model is available, we just have to scan using the 3D scanners. From there, we can get as a CAD model. Suppose if the part is not there or the shape is not there, then we have to invent or make a design concept. And from the design concept, we have to develop a 3D CAD modeling part. Once the model is ready, we are going for the analysis and optimization. And from there, we are converting into the .stl format. From there, we are going to the 3D printing and post-processing. Finally, the object will be used for the functional machine. This is the additive manufacturing process flow. I have discussed the creation of the virtual model. We can use AutoCAD, Creo, Solidworks, CAD, and any graphic softwares for initially creating the concept model. That is the computer-aided design model. The visual analysis we can use either using ANSYS, Console, Abacus, or SolidWorks. As I indicated earlier, that for a shoe sole, we can even model the leg, how the force is applied onto the shoe sole, and based on that, even we can select the material inside that shoe sole as a two partitions. One is your the front of portion of the sole, the another one is the back portion of the sole, that is the heel. Once we take that one, we can observe how we are.
Excuse me, sir. Sir, sorry for the disturbance.
Yeah.
I think you have minimized the shared slide, sir. So the shared slide which we are just watching here is not connecting with your words, sir.
Is it coming on?
We are watching.
I think whenever I'm going under projection mode, the problem is coming.
Sir, if you are minimizing it, then it won't be visible to us. So it would be great if.
Is it visible now?
Yeah, it is. It is slide number 6 is there, sir.
Yes. Anyway, I'll just go from here itself without going for the projection mode. I know that this problem is there. Whenever we go under projection mode, the Teams is creating a problem. Anyway, now you can observe it, the slide number 7.
Yes, sir. Yes, sir.
Yeah. Now the next process after creating the concept model and making it as a CAD model, computer-aided design model, and analyzing that one with the visual analysis. Once we feel that yes, it is ready for the fabrication, then we can go for the conversion of that model into the STL format, .stl format. The models are converted into standard triangle language, that is the STL, or standard tessellation language for the slicing process. Why this slicing process is required means our machine, we are first layer by layer on a horizontal plane we are completing, and we are going to the next plane. In this process, the different layers we are just making under slicing portion. The next one is the slicing and creating the supports. Here, the slicing process is done horizontally, as I discussed, for creating the different layers on a horizontal plane according to the layer thickness. For doing this particular slicing and creating supports, we have the Cura, Mesh Mixer, Blender. These are all the 3 softwares directly we can use for creating the slicing and supports. Now, once the model is sliced into the STL format, that one we can convert into the G code. This G code is very important for a 3D printer to locate the XYZ coordinates. Based on that, the connection, the path is generated to follow the each coordinate for doing the 3D printing operation or additive manufacturing operation. If you observe here, there are different layers, like the thick layer of one particular object, the another one is the thin layer for the other object. There is a tug of between the layer thickness and the process time. If you increase the layer thickness, the process time is very less. But the problem is that the quality is not good. It is not as a smooth structure. If we go with the more layer thickness, here we can get a better quality. Then here it takes more time. The resolution is high, and at the same time it takes more time. That is the, as we keep on decrease the thickness, we can observe over here. Like that, the object we can go under different thickness of layers for printing. The next one is the support. There are 2 things. Whatever the material we have, with that itself we can able to create the support. In the post processing, we have to remove this particular material, the support material of the object. But nowadays the water soluble materials are available. We can use those materials for supporting, and we can convert into as a part. We can print. Later on we can remove the support. It is simply, we can put it into the water. It will be water soluble material. This I have taken reference from Rajguru in 2020 in his published paper. Now, with this technology, as I discussed, I will be covering related to the Solidworks software as a computer-aided design part in the additive manufacturing. Normally, the earlier days, what the designers used to do is that they used to just read the drawing. Once if they understand the drawing, then they can able to represent the drawing as a particular concept and communicate that one to the fabricators. Here, the drawings are useful above all. That is true for representing the geometric form of the designed object. But the problem with the classical, the previous the technology is that the manual drawing we are making, and that one we are giving to the designers. But it takes a lot of time. That is one thing. And second thing is that whenever we lose the drawing sheet, that's all it is again a reprocess. To avoid this, the wastage of time and storing the required data into a database, the computer-aided, the digital technology has come to store the data and to transfer the data easily from one location to the other location. There, the computer-aided design has come into picture. Here, the computer-aided design, it is useful for the production of visual images by computer, that is computer graphics. It was first the important step in the development of computer-aided drafting and design. Both CAD, computer-aided design, or sometimes it is also named as computer-aided drafting. But altogether, I have kept this as a computer-aided drafting and design. It was made at the Massachusetts Institute of Technology in 1963. They have invented this one. They have used the sketchpad for development and demonstration of the computer-aided technology for drafting. You can observe here we have the computer processor that is displayed into the display system. There we have a light pen. By just moving that light pen, we can able to generate the coordinates, and these coordinates are stored into the memory as the drawing. We can even give the input to the computer with the help of a keyboard. And here we are on the cathode ray tube. We just using the light pen, we can able to generate the different coordinates of the drawing. It was just invented in 1963. Now the Dassault system, they have released this software as a Solidworks. It is solid modeling computer-aided design. The CAD software, it is computer-aided engineering computer program that runs on a Microsoft Windows operating system. The Solidworks was published by Dassault System. It is published, and the Dassault System is a European software company founded in 1981. Solidworks Corporation was founded in December 1993 by Massachusetts Institute of Technology by John Hitchcock. He was just founded this particular software. The SolidWorks is a feature-based parametric solid modeling design tool. There are three things. One is it is a feature-based. The second one is parametric. The third one is the solid-based design tool. Here, the feature-based means there are different features are there to model the 3D part. We can use the parameters, means the values. By values also we can able to change the solid model. And other than this, there is a relation between the different solid parts in the assembly. These are all the three features are included in the SolidWorks. Along with these three features, even we can able to do the preliminary assessment or preliminary analysis of the solid model before manufacturing it using the additive manufacturing technology. Now, which takes the advantage of easy to learn, the Windows graphical user interface, and it is a fully associative 3D solid models can be created with or without constraints while utilizing the automatic or user-defined relations. As I told, there are the relations we can able to generate between the different features as well as the different parts using the SolidWorks software. If you observe here, you can see that the SolidWorks window you can open. This is the window. There we can first go as a start and we can create the program, and from there we can open the SolidWorks from the file. Under this, there are three categories. We can create a part, we can go as an assembly, or we can make as a drawing file. In the part, we have to go as an individual part, and in the assembly, we can give the relations between the parts to form as the complete assembly. Once the assembly is ready, then we can go for the drawing for the future purpose. Otherwise, in the additive manufacturing, we can use the additive manufacturing technology using the either part. We can make the different parts together, and in the process of assembly, we can assemble them using the drawing. Now, here this SolidWorks window, I have just given over here the different windows or toolbars available in this SolidWorks. The first one is the menu bar. The topmost horizontal bar is the menu bar, where the set of most frequently used tool buttons are available over here. And the second one is the different toolbars are there. Under these toolbars, we have the sketch toolbar for sketching that one into 2D and creating as a features into the 3-dimensional space. And assembly is there for connecting all the parts together to form as an assembly. Even we can validate the dimensions, whether the tolerance and fits are all right or not using the dimensional expert, and we can go for the simulation tab for doing the visual analysis before making the part using the additive technology or 3D printing. Now, the third one is the command manager. This is the most important part, that is the command manager. Here we have a different command, like the tools are available as icons. We can select different features or sketch entities and all for creating the 3D parts. Once the parts are ready, we can give the relation to them to form as an assembly. The fourth one is the configuration manager. Here, the fourth one, if you observe the configuration manager, it is the means for creating or selecting or viewing the multiple configurations of the part or assemblies in a document. The fifth one is the property manager. Here in the property manager, we can see what is the property of each part or each feature in the model under this particular property. Now we got the feature manager. The sixth one is the feature manager. We can see the different features which are available over here. Like we have a extrude feature, revolve feature. These are all any computer aided design software is having for converting the two-dimensional drawings into the three-dimensional models. The seventh one is feature manager design tree. The user directly can able to modify these features for modeling the part. These parts can be modified or change the dimensions using the feature manager design tree. That is the seventh one. And the eighth one is the status bar. We can observe what process we are doing or any simulation, what is the status of the simulation. All those things we can observe under the bottommost horizontal bar. That is the status bar. Now the ninth one is the heads up view toolbar. Inside this graphics area, the frequent operations like zoom in, zoom out, and the sectional view orientations and the view type and all those things we can change using the heads up view toolbar. It is just above the gray area. That is the graphics area in the SolidWorks environment. Now the 10th one is the SolidWorks search. It is available over here. We can directly search the different options which are available in the SolidWorks software. The 11th one is the help layout. Even we can connect that one to the internet or using the web browser. Also, we can see different help features of the SolidWorks. The last most one, the 12th one is the task pan. Here, under this task pan, here you can observe this is the task pan. The important task, like we can connect into the library materials for selecting different materials. Even the different view orientations also we can get from here. And in this case, we can see we can change the appearance of the different parts, and the properties also we can put as an input into the task pan. The 13th, the lastmost one is this one, the graphics area. Whatever the modifications we are doing as a parametric means by giving the input as a values, we can able to get the complete model that we can visualize in the user interface. That is the graphics area. But the entire thing we are modeling using the different icons on the GUI. Now, why we have to go for the SolidWorks? There are other softwares are also available, but the base we have considered as the AutoCAD for the comparison with the SolidWorks. A drawing on documents. If you observe this one, in the SolidWorks we can use the 3D parts and assemblies we can generate from the 2D drawings. If 2D drawings are there, we can generate into the 3D parts in the SolidWorks. But in the AutoCAD, it is not possible. We have to go from the 2D lines, and from there only we can able to make the drawing. Or for the modeling, we just have to go as an individual extrude or revolve options. From that only we can do in the AutoCAD. And drafting, here in the drafting we have the sketch tools. In AutoCAD we have the draw tools. And these are all the basic simple procedure only. And precision placement of entities, if you observe in SolidWorks, all the two-dimensional entities are available. Those entities we can construct for making as a two-dimensional sketch. For this two-dimensional sketch, we can give the relations and we can give the dimensions. In AutoCAD, the line or other entities at full size are placed for making the sketch. Annotations. In AutoCAD, we have only nodes and blocks, but in SolidWorks, we have nodes, blocks, and other annotations. The relations also we can give, and from there we can able to animate and see how the particular component is functioning. If you go with the printouts, we can directly take the printout from any mode in the SolidWorks. But here in the AutoCAD, we have to go with the plots under layout for printing the drawing. Now, these are all the different icons are available for the sketch entities. We just have to start the program. Under that, the SolidWorks, we have the file, the new part, and we can able to make as a part. And from there, using the sketch entities like sketch or 3D sketch, both the options are available for sketching. Under the sketch entities, we have the line, underline, line is there, center line is there. We can give the dimensions using the smart dimension, horizontal dimension, vertical, and even the horizontal and vertical coordinate dimensions also we can provide using the dimensioning. For the rectangle, we have the corner rectangle, center rectangle, 3-point rectangle, and the 3-point center rectangle, parallelogram. These features are available under rectangle. Circle, we have the circle, perimeter circle, we have arc and tangent arc, 3-point arc is there. Ellipse, also we have ellipse and parabola, and partial ellipse options are available. The spline option is also available. For spline, the spline you can make as a freehand spline, and equation driven spline and fit spline. These options are available. The polygon is the major particular entity is available. Using that, we can make the multi-phase polygon like triangle, octagon, hexagon. All these polygons we can make using the polygon. There is a special feature called slots. We can make the slots for the keyways using the slot option. The plane is also available, and we can give as a annotation for the text, and point also we can locate in the software. Here, the basic features, the entity operations, as we have in the AutoCAD also, we have the sketch fillet, sketch chamfer, trim and extend options are available. The convert entities, we can convert the 2D surface as a outer boundary from the 3-dimensional model. We can have an entity operation like offset, mirror entities. These options are also available. Now, for creating any model, there are other basic features like we can copy the entities, we can paste the entities, we can move and change the scale of the entities, we can fetch the entities also. The other operations like the linear or circular sketch patterns. Suppose if you want to make the multiple sketches along XY coordinate system, we have linear sketch patterns. Along about polar coordinate system, we have the circular sketch pattern. These two features, two entities are available under linear or circular sketch patterns. The quick snaps. Anyway, while making one sketch, one entity to the another entity, the connection, we have the quick snaps for giving as a connection, like the point snap, center point, midpoint. All these options are also available. Now, using these options, I will just show you in the SolidWorks environment also how we can use with a simple model. Once we use all these entities, we can make the two-dimensional sketches. Remember. Now these two-dimensional sketches we are converting into the three-dimensional models. The two-dimensional sketches and three-dimensional models, there is a variation. The reason is that whatever we are existing in the environment is a three-dimensional environment. But to represent this three-dimensional environment, nowadays we have the computational power with virtual space we can able to show. But as a paper, as a document, we want to transfer to somebody, we have to make it onto the paper as a two-dimensional drawing. For converting the three-dimensional units into the two-dimensional drawing, we have the representation of the orthographic projections and isometric projections. I hope that all of you know about these orthographic views and isometric views. In the orthographic views, we have basically the first angle and third angle projection. In the first angle, we have the front view on the top and the top view at the bottom, and the side views are there, both the sets of your front view. And in the third angle projection, we have the front view at the bottom and top view at the top, and both the side views we have left and right side of the front view. That we can only have first angle and third angle, as we know already that there won't be any second angle and fourth angle exist because of the rotation of the plane in clockwise direction. Now, if we see that is the previous one, we can show as a two-dimensional plane. Even under the two-dimensional plane, we can show the three-dimensional part also using the isometric view. Here, all the axes we are dividing equally. That is why it is called as isometric view. So each angle we can divide into total 360 degrees divided by 3, 120 degrees. We can represent the three-dimensional part onto a two-dimensional plane. For that, we have the isometric view. Now, in the SolidWorks, for converting the two-dimensional sketches, the entities which are forming the sketch into the three-dimensional model, we have the extrude face option or extrude boss option. We can extrude the thing along as a depth. We can give the revolve. We can revolve under a polar coordinate system. Using the spline, we can either sweep or sweep the option. The loft is also there. Under that loft, with a different cross section of the objects, like the shape is different on one plane to the other plane, from a rectangle to the circular, from one plane to the another plane, we can loft it. Means we can form it using the loft option. Now, even there are removal, like not only the addition, even the removal. The virtual world, we can remove the material. That won't create any cost rather than little processing time. But in the actual process, if you remove the material, it takes a lot of wastage of the material. And anyway, it won't come under as a additive manufacturing. For that additive manufacturing process, we just have to remove the material also based on our shape requirement. For that, we have the extruded cut option, a revolve cut option, swept cut option, loft cut option. Directly in the virtual world, we can remove the material also. Now, here, like the features, these are all called features in three-dimensional space. These features, for these features also, we have the feature operations. Like we have the fillet, chamfer, ridge, scale, shell, draft. These options are available. Fillet is the whenever the corner is there. Remember, while manufacturing, we should not keep the sharp corners because they may damage while handling. The handling process. While handling, it may damage the operator. That is why, or it may create inconvenience to the operator. Always the best process is that the sharp corners we have to make it as a curved surfaces. That is called fillet. Sometimes even we can make them as a flat. That is chamfering. The rib is provided very important thing in manufacturing, that if the strength is not sufficient for the particular part, we can put as a rib. That rib that will act as a stiffener and give the strength of the. It will add to the strength of the object. Sometimes we have one particular part, we have to scale it down in, suppose there is a very big the structure that we want to make it as a monument for display. Even we can directly scale down that one and we can give to the 3D printer for printing it. And the shell. Shell is the most important feature here. We can remove the material and make it as the outer shell part. The draft is also the another option. We can give the draft angle and we can just take the section from one scale to the another scale with the draft feature. Now, in features also, we have the linear pattern along x-axis and y-axis as a Cartesian coordinate system. We can keep the multiple objects. The circular pattern along polar axis also, we can keep the different patterns as a about polar axis, the same whatever the object we have created. The mirror features, if there is a feature exactly we want it as a symmetrical feature, then we have the mirror option. There is option curve driven also. Following the curve also, we can keep the multiple features. The sketch driven pattern is also there. By clicking the different points, we can keep the objects at different locations. The table driven, by giving the values of rows and columns, we can make the pattern. Like we have fill, split, combine, join. These are all the additional features. With that, we can able to fill the two parts or two features. We can split the features and even we can join these features. Now, along with that, as a reference, if we have a reference geometry, the plane, axis, coordinate system, point, the basic geometrical features are also available. And curves, we have the spline, split line, the project curve. We have the curve to XYZ points. The composite curve is there, and helix and the spiral. These curves are also available. Using this helix and spiral curves, it will be very easy for a user to generate the spring or thread of a board. All these things we can able to generate using the helix feature along with the your spline option. Now, even for the display, how the display should be there for the computer aided model, we have the wireframe model and shaded with edges, shaded. All these features are available. Even the zoom out and zoom in options also we can observe using the third one. If you make this particular part, actually I have done this one for one implement. This is called as a cultivator. Most of we know that. Here I have modeled using the Solidworks software, and later on I have printed the individual part and assembled as the complete structure. Here the complex assemblies, whatever the thing is there, we cannot able to go directly with as a assembly modeling. Initially we have to make the part modeling, and once the parts are all the parts are ready, we can connect them with the mates. Mates is an option by which we can give a relationship between different parts. and it is very useful. We can even make an animated video of how we are assembling the part A with part B, and that is very useful while doing the assembly process by the fabrication team. It will be as a guide. We can make using this video files also using this particular option. Now there are two ways of designing. One is the bottom up design, the another one is the top down design. In the bottom up design, initially we have all the parts, means we have modeled the parts, and we are assembling these parts to form as an assembly from the bottom to the top. That is why it is called as bottom up approach. In the top down approach, we don't have any part. We just have to form it as with a logic or with a concept how the part should be. It is as an entirely new design, and there we just create an assembly, and from the assembly, by seeing the part A, we are forming the part A, and to according to the surface of the part A, we are making the part B. Means there is a relation is coming from top to down. That is why it is called as top down approach. These two features are the two approaches are available in the SolidWorks while making an assembly, and the mates are the these are creating the geometric relations between the different parts. The relations are like the coincident, perpendicular, tangent. These are all the basic geometrical features. Along with that, we have the mechanical features also, like as a cam and follower relation, gear mate relation, and we can give as a the belt and pulley relation. All these relations are available in the SolidWorks. Therefore, it will be very useful in the beginning itself. We can simulate the models, and based on the functionality, we can go for the manufacturing. How we can do that one, I just mentioned as the procedure over here. And as I told earlier, in the different mate options, the general mate options, we have the standard mate options, like we can coincide, we can make as a parallel, perpendicular, tangent, concentric, log, distance, angle. These are all the options are available under standard mates. And we have the advanced mates. In the advanced mates also, we can make as a symmetry, we can give certain width between the two parts, and we can even make them as a path. Suppose there is a path, along the path there are different features should be there. There we can use this path mate. For example, the pin is moving inside the slot. For that we can use this path mate option. And there is a linear or linear coupler option is also available. Whenever the line is passing along with a linear entity, there we can use the linear or coupler option. We can give the limit as a linear limit between the two parts. We can give the distance, and even the angular limit also we can give. Means while giving as a motion, it will be kept as a limit, as a lower limit and upper limit along the linear axis, that is the linear limit. Even along the rotational axis as an angular limit also we can able to give using this SolidWorks. And along with that, we have the mechanical mates also. For machine components, it is very important to give the relation between two parts. The relations are like the cam. Under this cam, like we have a component as a follower, the other component as a cam. Between these two, we can give as a relation. The relation is that the follower has to follow the profile of the cam. And we have the gear mate. Very easy using the SolidWorks. We have to just select both the two gears, and once we mesh both the gears together, and we need to give what is the pitch and number of teeth. Based on that, we can able to give the motion between the two gears. Otherwise, the other option is that we can give the speed of the input gear to the output gear ratio. From there also, as a gear ratio, we can get the motion. And we have the hinge joint. The hinge joint, it has only the rotation. It does not have any translation along x and y axis. The rack and pinion arrangement, here we have a rotation along z axis, and it can move along x axis. Only 2 degrees of freedom also we can able to create. The screw is there as like a bolt and nut arrangement. It will follow as a screw. It is 1 degree of freedom. The universal joint, it has 3 degrees of freedom. Now, the difference I am showing between the part and an assembly, actually I have made this particular part as a part drawing. This is actually the robot, the base. On that, the robotic arm base. On this arm base, we are mounting the different components, like the robot fingers and the actuators and all with the servo motor. This is the base drawing, that is the part drawing of the robot base. And this is the assembly drawing. In the assembly drawing, as we know that we need to list out the different parts which are there in the assembly, and we need to even indicate how many components are there in this particular assembly. Actually, this is the assembly we have made as a robotic arm for our purpose for handling of the parts. There we have fabricated using this 3D printing technology, and different components we have made initially, and later on assembly we have connected manually with this assembly. This is the assembly drawing. Once the drawing is ready, then it is important to analyze that. The model is ready. It is very important to analyze that whether it will sustain the load or not. That is important. Suppose I have a particular drawing, like an AutoCAD, I can make the drawing and directly I can go for the 3D printing or additive manufacturing. Once the part has come, I have kept it into the direct application. During the application, sometimes it may fail because of the load. That is why it is very important to know the basic strength of materials of the knowledge for manufacturing, that whether the part, whatever we have made, is it included with the design concept and analysis or not, we need to check. Now, as we know, there are basic different theories are available. Like if we consider that the displacement force, the plot, otherwise this is also like our stress and strain plot. We need to just check whether the stress and strain, what is the relationship between these two. If it is a proportional limit, that is we have the stress is directly proportional to the strain. That is the Hooke's law we can follow. That will be going under the linear analysis. And if it is not going this particular proportional limit, we have the nonlinear analysis. Sometimes for a given small amount of displacement, the stress may be very high, or for the small amount of force, the displacement will be very more. That is why we need to just check the property of the material, whether it is a isotropic or polytropic material, or anyway the composites, they are having the different properties. We can just check. In the SolidWorks software, the option is available over here for the static analysis is the linear static analysis. Using this linear static analysis, we can able to calculate the displacements, strains, stresses, and reaction forces also we can able to calculate. And finally, we can able to get the plots of our factor of safety. Now, once the factor of safety plot is there, from that we can able to just check whether the design, whatever we have made, it will sustain the load or not. That means our factor of safety should be, theoretically, it should be more than one for a better design. Normally, we are considering it should be as minimum as 2.5. But anyway, if you go with as a more factor of safety, there is another aspect, the increase in the cost of addition of the material. Now, considering that as per the Hooke's law, we can go as a linear assumptions that the load is directly proportional to the induced response, that is the displacement. Here, for any basic structural design or any basic static analysis, the process is that initially we can make as a CAD model. Under that CAD model, we just have to go with the boundary conditions. Boundary conditions means the fixtures. We just have to fix where the part is in contact with the ground. Otherwise, for example, the robotic arm. The robotic arm, the fingers are actuated. Once they are just holding the load, they are resting onto the base. That means wherever the each link is connected to the base, there we have to give the boundary conditions. And now the fingers are actuated and they are just holding the load of the object. There we just have to calculate how much force is required to hold a particular object. Now that force we have to give as a initial condition. By giving the boundary conditions and initial conditions and giving the material properties, another important aspect. We directly visual world, we can indicate what is the material of that particular object. Now giving all these three, we have to mesh it. The meshing is the main aspect in the simulation part. It is the disintegration of the entire complex structure into the known elements. There are different three-dimensional elements or two-dimensional elements are there, like a cube or 8-noded brick. These are all the finite element concepts also we need to just consider. Once the finite element concepts we know that, and from there we are meshing the entire structure or the object, so that we are giving the boundary conditions and initial conditions, and from there we can able to simulate with the material. Now during the simulation we can get initially the displacement, because we have given the stress is directly proportional to strain and stress relationship is your here modulus of elasticity in a one-dimensional part. Once we know the strain, again strain is the change in displacement per unit length. From there we can get the displacements. From the displacements we are calculating back to the strain, and from the strain we are calculating back to the stresses. This is the finite element concept. Using the finite element concepts we can able to calculate stress, strain and displacements. Now there is a factor of safety plot. In the factor of safety plot, this is the factor of safety is the ratio between the strength of the material to the induced stress in the object. From that, we can able to calculate the factor of safety, and the plot will be coming directly in the SolidWorks. We can observe the factor of safety should be always more than the 1 or 2.5, whichever the designer is intended to fabricate the component. This is the basic outline of the entire thing. I'm just planning to show that one into a particular model, what I have made in the SolidWorks software. I will be showing that one after this one. These are the references I have considered for the additive manufacturing. Okay. Before that, I'll just show in my SolidWorks by sharing the SolidWorks window how I can model a particular component and do the stress analysis. I'm just yeah, I'm sharing this one. Let me share that part. I'm just opening this one. Yeah, this is the one. I hope it is visible to all of you.
No, sir, not yet, sir.
Now?
Sir, is there the red boundary line is visible on your display, whatever you are sharing?
Which one?
On the sharing screen. If you are watching the red boundary line, which is covering the
Okay,
whole.
I'm just sharing the entire thing.
Yes.
Is it visible now?
Yeah. Yes, sir. Right now it is visible.
Okay, anyway, now it is the SolidWorks is also running, and yeah, I hope the entire thing is visible to you. Here,
Yes, sir.
this is actually the assembly I have made for the Cultivator Tine assembly. It has the different parts. Like I have a clamp block. I'm clamping this one to the main assembly to the frame, and this is the Tine. Tine is available, and this is the shovel, and this is the U clamp, and this is the clamp plate. I have just taken the small assembly. This assembly will be connected to the main assembly, that is the entire cultivator. In this, the small assembly, the each component I can show you how I have made. I'm just opening this component. Yes, this one is the clamp block I have modeled using the SolidWorks. You can observe that in the SolidWorks we have the sketch entities. In the sketch entities, we can make a new sketch, the smart dimension, the line, triangle, slotted bar, circle, the arc, and the polygon, spline, ellipse. All these options are available. Even the annotation, we can give the text over there. We can convert the entities. This is the tab, the sketch tab. We can able to use these entities and entity operations for making a 2D sketch. The second tab is the features. Using the features tab, we can use the different features like extrude, revolve, swept, locked, all these options we can use, like extrude cut for removing the material visually, hold wizard, revolve cut, sweep, locked, all these options are available. You can use this one for making the entire component in the visual world. I will just show you. Initially, the first feature I have used as the boss or extrude. I will just show the first what I have made. This is the direct boss or extrude I have made. For this, I am using the sketch. This is the sketch I have created. You can observe the sketch here. This is the sketch I have made initially with the given dimensions using the rectangle and circle entities. I have created this particular sketch. Now, once the sketch is ready, I am coming out from the sketch and I am giving the extrude option. Under this extrude option, I will just show you how I have given this extrude, how much magnitude and all. You can observe this one in the isometric view. Yes, here the extrude length I have given as 40 millimeter. As per the object shape, like 107 millimeter is the total height and 45 millimeter is the width, and the diameters we have 18 millimeter for all the four holes, and they are located from the center as the 75 millimeter symmetrically and from the central axis. Now for this one, I am giving the extrude as 40 millimeter. The 40 millimeter also I have given. This is the particular object I have made. This is the clamp block. The first feature I have used as boss or extrude. Now with the first feature, I am going with the addition of the second feature. Now once I add the second feature, earlier there was no cut at the back. Means I am removing the material in the visual space itself, in the visual model itself. For this particular cut extrude option, I have used the under sketch. The sketch also I will show you. I have selected the top surface as a reference plane, and from there I have created the sketch of 7 millimeter, and it is symmetrical to both the sides of the center axis, and 5 millimeter is the height. I have removed this particular part in the visual space itself. That is why now the part got removed. This is the second feature. That is the extrude cut is the second feature. The first feature is the extrude. Now I am giving the third feature. Again, that is also an extrude cut, where I am just giving that one. I will show you in the isometric view. In the isometric view, the V cut. The V cut I have created using my extrude cut feature. This is the sketch I have created on this particular plane, and I have extruded through all. For making any CAD model, the computer aided design model, our visualization should think what all the different features are required to create this particular part. That means even the 3D scanner, whenever we are scanning the object, it is just locating all the coordinates and forming it as a CAD model or CAD file. It is scanning. Similarly, we have to just visualize and think by which feature I can able to create this particular part. And I am cutting this one through hole. This is the final part I am getting as my clamp block. Here, the different orientations I can show using the software. I can show you all the three views, like my front view, the left view, and top view, and the trimetric view. Like isometric view, here the trimetric view is there. If we want to see the isometric view, the isometric view option is also available under this software. We can show under a isometric view also. All the three views are available. Even the display, I have given the color as a the red color, light red color. Even we can change the color option, or even we can change the view, the visibility option. Actually, it is a shaded with edges. All the edges I am showing. Suppose as a drawing, we can observe as a drawing part format also. Even the hidden lines should be solid, means we can observe that part also. But anyway, in the drawing, we are just going, the hidden lines are visible with the dotted lines. The outer boundary is the solid line. That feature we can able to keep. Suppose to change this color of this particular part here, the color feature is available. We can change the appearance, not only the color, even the other materials also we can add directly using this feature. We can set the different materials are available over here in the library, or even we can change the color also of the particular object. Now, using these features, we can able to, don't want to save. Now I'm coming back to my assembly. Which are the thing I'm updating? The updated part will be directly modified in the assembly. That is the advantage of this particular software. There is no need to go again change the assembly. There is a relation I am keeping between the different parts. Automatically the part will be updated. Like we have the clamp block I have made, the Tine also I have made as a part, the shovel as a part, U-clamp and clamp plate. These are all the different parts we can model initially, and we can assemble all these things using the relations. If you observe the relations over here, as I discussed earlier, we have the different relations in the assembly. The relations are like we have a basic mates, the mid different faces we can make. Those are all there under the standard mates, and we have the advanced limits also. The advanced limits, under the advanced limits, we have uh, like this profile center, symmetry, width, all the options are also there available. Advanced limits, if we want to go for the standard limits, coincident, parallel, triangular, these limits are available. And the mechanical limits I want to show. In the mechanical limits, we have the camera arrangement whenever it is just connected. Anyway, it is as a rigid body, the Tine assembly. I have not used the mechanical limits. Suppose I want to simulate this one for the motion analysis. There we have to give the options of the mechanical limits. Now this is the assembly structure. The entire assembly, after creating this one, we can go for the simulation tab. If you go with the simulation study, here the simulation tab is available. Under that simulation tab, I have selected the static analysis. The static analysis, you can observe, as I told earlier, I have selected the materials like the clamp block, alloy steel, clamp plate, shovel, Tine, U-clamp, two U-clamps I am using over here. Both the U-clamps I have converted into the alloy steel. Once I give the, see, in the SolidWorks, the upper portion is the modeling part, the lower portion is my uh, simulation part. Both the things I can do using this particular software. Now, in the parts, by giving the different materials, the boundary conditions where it is going to get connected to the main assembly, I have given those surfaces as my boundary surfaces, means I am fixing all the surfaces for my boundary condition. The next one is the load. The load, the initial conditions. The initial conditions, the how much force is acting, that is actually the parallel. When the Tine is moving forward, the load is acting opposite to the direction of motion, parallel to the ground. See, the same load applications also have indicated onto the Tine over here under the fixed the load condition. Here I have taken as a 60 kg force or 600 Newton. I have given the value as the force. I have selected how I have given the force also. I am just showing you. I have selected the face as a reference face. I have taken to that face. I am putting as the normal load 600 Newton. I have given. Not only the load, the option is available over here to give the torque also, or the different how much torque is applied onto the surface based on our object. We can give the torque. The other options also we can provide as a torque. Once we give the torque option, the torque how much torque we are going to give, that will be asking, and that also we can able to give over there as a torque. Now once the force, that is initial and boundary conditions, are given into the model, initial and boundary conditions once we specify into the model, then we have to go for the meshing. Under this meshing, we are going to create as a mesh. Here under this mesh, we can generate the mesh and we can able to create the results by running this. Already the mesh got created. I'm just showing the mesh option over here. By clicking the run button, we can able to generate the mesh and get the result. I have kept the medium mesh. If I go with the fine mesh, it takes the time. That is why whatever the time constraint of that, accordingly I have kept the mesh. But anyway, the result we will get as the approximate result as the solution. Once this we run the static simulation study as a linear static study in the Solidworks software, we can able to get the result, and plots also we can able to generate from this particular software. Yes, after running this one, we can see the plots. The one with the stresses are there. Directly we are getting as the stress plot. The displacement plot, and we can get strain plot, and also we can observe the factor of safety plot. All these features we can options we just have to put as a post processing of any the simulation software like ANSYS and all. I have already kept as inbuilt what are the results I want, and accordingly I can able to generate these plots. Now the factor of safety plot, if you observe, the factor of safety is starting from 13 to 4000. That means it is more than one. I will assure that the design is safe from the factor of safety plot. This is the factor of safety plot, and in the stress plot we can observe because of the load how it is going to get the different stresses we can able to observe in this particular case. The strain. This is actually the strain plot. We can observe. We know that the strain is maximum at the fixed end. Wherever we are just fixing, it is like as a cantilever beam. The load is applied at one end, and at the fixed end we can observe the strain is maximum and also the stress is maximum. We can see now the stress plot. We can see the one with the stress. The minimum stress is 132 pascals. The maximum stress is going 376 megapascals. No, 37 megapascals. 37.65 10 to the power of 6 pascal. That is 37 megapascals. And based on the strength of this particular thing, what we can get is that the factor of safety is changing from 13 to 4695. From this, we can observe that the design is safe. Directly, we can use for the different parts for manufacturing, either using the metal molding, or directly we can go with additive manufacturing with the metal processing. Now, once this study is there, we can even able to generate the report of what the stress we are getting and how the boundary conditions we are giving. Once we publish the report, directly we can get an option to publish the result of the analysis for later verification. That option is also provided in this particular software. I hope you can see the result. Is it visible as a document?
Sir, document is not visible, sir.
Not visible. Okay, I'm just showing in the another format. Is it visible now?
Yes, sir, it's visible now.
Yeah, whatever the simulation I have done for the Tine assembly, it got generated as a file. We can observe the boundary conditions and initial conditions in the CAD model. The visual simulation we can observe. Here, the metal property of each unit is also located over here, as each unit is treated as a solid body. And for that, based on the alloy style, the mass we can see, volume, density, all those things also we can get from the simulation. It is very useful for assessing later part. I mean, how much material is required for fabricating, or how many bundles of your the particular material is required. We can able to assess at the beginning using the Solidworks software. Now here the different properties, as you can observe, the static analysis I have done. Uh, Under the static analysis, I am using anyway the SI unit system. These are all my material properties. The alloy steel I have taken for each particular component. Uh, the carbon steel I have used for my shovel. The shovel I have used carbon steel because most times is required. That is the direct contacting material for the soil, contacting tool for the soil to break. And the boundary conditions I have given. These are all the fixed boundary conditions. This is the force I have applied. The force I have applied is 600 Newton along the axis, Z axis, and that is a 600 Newton force. Okay. Now we can observe here that the global contact also we have just given. What are the different contacts are there in this particular model, and we can even show that different the mesh properties. The solid mesh we have created with the 4-point Jacobian points. These are all the finite element concepts. The element size, the minimum I have taken 0.5 tolerance, and it is going as 10.05 millimeter. The element size. Here we can see the mesh information, the total number of nodes and total elements also we can observe, and finally we can get the result that this is the mesh part, and this is my stress. The stress values also we can observe the maximum and minimum stress values. Minimum is 132 pascals and maximum is 37 megapascals at node number 69 as per my finite element analysis. Similarly, we can get the displacement also. The maximum displacement, this is one more important thing. Normally, whenever we design, we will see only the stress as a one mixed stress or factor of 50. Even though the structure may not fail, but it should not give proper, the deflection is also very important. Suppose I have designed a structure and it is not failing, the material I have selected as a more elastic, but it is giving as a deflection as 5 millimeter or 10 millimeter. There, the 10 millimeter is not advisable, because once we deflect, it cannot able to give the load to fill the soil, suppose in this particular machine component. That is why the deflection is also very important. We have to see always the maximum deflection, that is 0.281 millimeter. It is advisable, we can go directly with the design. If it is not, if it is more, then we have to change the cross section, that is the optimization. We can go with a different cross section of the Tine and different sectional properties of the other elements or other components. With that, we can finalize the design optimization to get the complete component. Now, this is the strain. In a strain component is also there over here. And finally, the factor of safety, as I told you, it is the minimum factor of safety is 13. So I'm considering that the design is safe, and we can go for the direct fabrication using the additive manufacturing. Now, this is the simulation part. Come back to the model part. Now, this is the model. Once the model is the CAD model we have created, and we have done all the simulation analysis, we can save this model as a STL file in the SolidWorks. There are different file options are available. We can directly save this file as a save as, We have the options. The part as SLD part option is available in Solidworks. There are different options are there for saving this the part for based on the compatibility. We can go with the .scat file or .vda file or even directly we can go ahead with .stl file for our 3D printing. Once we go with the .stl file for the 3D printing, directly I can save this part and it will be generated. It is showing that the triangle is 392. You can observe that. You can even modify also. These are the different triangles are generated for this particular STL file, and we can save this. Once we saving this one, the part will be saved into the space, the directory, and this particular component we can take into the 3D printer. There anyway, the user interface will be available to place the part onto the platform or printing space. From there, we can able to print the component. Now, this is the thing I want to just present in terms of the technology of 3D printing. Using that one, how we can able to model the components, and we can assess that one. And finally, once it is the proof is there for the design, we can directly go for the 3D printing. With that, I'm very much thankful to the organizers of the faculty development program. I hope that I have given enough input. It may be very useful. Later part, it is not the end. We can again explore more about the thing. And in 2020 version, directly we can have the option like even we can create a G code and supports also we can create using the SolidWorks. We can use this software and we can go forward for the additive manufacturing using different printers. Thank you very much. If you have any queries related to my talk, I welcome you.
Thank you very much, sir. The purpose of education is to make good human beings with skill and expertise. Enlightened human beings can be created by teachers, said by Dr. APJ Abdul Kalam. You fulfilled his words today, sir. Such a wonderful session we got today, especially the end of the session. We got the demo and example of your stress analysis and simulation. So informative. Thank you very much, sir.
Thank you very much to the team.
Now the question and session.
Thank you, sir, for such an informative and such a nice presentation. We will take some questions. We will not take much because we are actually we have to schedule it on the time. So first question is from one of our participants, which is which are the materials are in utilization in agricultural equipments nowadays?
Okay, very good part. Agricultural materials itself is very vast, changing from actually my domain is related to the mechanical engineering applications in agriculture. Like that, we have like the other domains also, like civil engineering applications, chemical engineering applications in agriculture. I'm just looking after the manufacturing of the components like machines of agriculture machines. Related to this one, we are just going with the carbon composites is the future. We are planning to apply that one. And other than that, all the metals, these are all the existing, the industries, they are going with the existing materials. Now, the thing is there, they want to go for the carbon composites. The composites, the next feature is that they are replacing all the metal bodies or cast iron, alloy steels and all with the carbon composites. The studies are going on. Once the strength is fulfilled, the use of the carbon, the composites is that we can make a light structures and easily we can handle like a sickle and all the things are available, but they are made up of the metal and wood, the existing. We just if we transform that one using the 3D printing technology with the existing materials, thereby we can make the lighter materials with the carbon anode, carbon composites, and the strength is also achieved. And only the fabrication is an important, the serrated section that we need to just think. Based on that, it will be as a very easy tool and easy to handle for harvesting the crop and picking the fruits Even the robotics are also we are using. There also we can go for this particular materials. But we have to just motivate the industries to come into these technologies. Anyway, it is started now. Then there are a lot more studies we need to just check what are the feasible materials based on the availability and functionality of the agricultural machines.
Sir, we will take one more question. This is also from one participant. Which is the most effective additive manufacturing technology in agricultural application?
Yeah, the most effective. Okay, in the agricultural application, we are just as of now starting that one, and we are using the FDM technology. Okay, but anyway, nowadays the other technologies are also there. Mostly the agriculture and food is combined together. When we go for the food processing and all, now we need to just think about the liquid deposition as a food material, and even the laser printing. The laser printing technology is also very much useful for cutting the different tools based on the shape. These are all the technologies we can employ in in our 3D printing.
Thank you so much, sir. It was a very wonderful experience with us. Thank you, sir.
Okay, thank you. It is only the beginning. Surely I will let you know the whoever have asked me the questions. You can contact me. It is only the beginning of the use of this technology in agriculture. Surely we will just check that one, and I will intimate you the different ways by which we can able to fabricate the machines. Thank you very much.
Sure, sure.
Okay, thank you. I'm just closing this one.
Thank you very much, sir.